I can do that and edit it into the file. Okay, so we've got a brief introduction to SWM. And what I stated was that most of the components in HEC-HMS, there are SWM equivalents, with the exception of the transformation model. SWM has that capability, but it has to be explicitly supplied from external data. And we will examine that in a future lesson. So for today, we want to try two examples. We're going to want to do this one, and then the second example would be the Ash Creek. I'll be going to the shared hydrosite in a second. In talking about the SCS type storm as just an example. So unlike HEC-HMS, SWM doesn't have any of this type storm stuff built in. You, the operator, have to supply that information. So oftentimes I found it useful to take the type storm out of HEC-HMS and supply it to SWM. SWM is a useful tool when the hydraulics matters, when you're actually having to ask hydraulic questions. I personally think it's superior to a HEC-HMS, HEC-RAS combined model for that case, but that's another alternative that one could use. So I'm going to grab this type storm out of HEC-HMS and drop it into SWM. That'll be a useful skill for you to see happen. But SWM doesn't have any kind of type storms built into it. The second part, since that was all done externally, we'll just be able to drag and drop directly. We've already done the processing for these data for HEC-HMS, and we can use the same data for SWM. One other thing I want to mention before I continue is, last lesson I was complaining about the software, but it turned out it was me. I was making a mistake with HEC-HMS, and I left an extension to the video where I finally figured that out. So when I go ranting on software, sometimes I'm wrong. So let's go to the simulation environment. And I hope it's still running. I didn't reboot it over the weekend like I usually do, so we'll find out in a second. Okay, this is developer. Well, that's a good sign. So at least the development part is working. And it looks like I have some station identification information. Okay, so we're going to start with SWM. And I will actually probably do an introduction to the software itself, because I don't know how many people have had prior experience with SWM. If I look at the list of people, I think a couple of you had water systems from me a long time ago, so you have seen SWM at least once. In theory, you've used it, but it may be a team member on your homework team did all the work, so you may not actually have much recent experience. So this is the SWM graphical user interface. There's other ways to access the program. If you know how to build an input file, you don't need to use this interface. And as an aside, I have a completely online SWM modeling tool that if you supply it with input files, it'll run it for you. And that's used for simulations that maybe take 8 or 10 minutes to run. You can do that here in this environment, but waiting on a GUI for 10 minutes, most people give up and they delete it thinking they made a mistake, when in fact they didn't. So this area that I have moving around is called the study area map in the SWM graphical user interface. In HEC-HMS, the equivalent, I believe, is called the drawing canvas. Jargon. When the desktop manager is working right, like it is right now, you can resize it by grabbing the corner. This button will shrinkify it, and that one will restore it, and then the dreaded X button will delete it. And then somewhere up in the menu, it's probably under View, you can recover the study area map. There's a set of icons at the top. It's exactly like a McDonald's picture menu. In fact,
hey, Dr. Cleveland?
Yes?
Can you maybe share your screen?
Oh. I wish you told me that sooner. Sure. That's hilarious. So I'm just babbling away, and there we go. And this is going to be the worst video of the course so far. Well, you got to have a. Okay, so I'm going to have some editing to do on the video. I may actually remake the entire thing from scratch, but I'll leave the recorder running in case I make mistakes so I can catch it. I have an idea. Can everybody see my screen? Do you see a window with a graphical user interface that says SWM 5.1 on the top?
Yes.
Yes? Okay, so that was one yes. 4 to go. I'll assume, John, I'll give you the, whoever commented, John, I'll give you the yes, or Ian, I can't remember who, so that's 2 yeses. Okay.
I'll say yes too.
Okay, thank you. Perfect. I will go with that. I have that working. It's definitely a Monday, isn't it? Oh, y'all don't have to be silent on that. All right. Okay, come on, screen. Give me real. Let me have control back. There we go. So let me start over again. This is the SWM interface, and the area that's moving around is the study area map. In HMS, its equivalent is called the drawing canvas. And there's similar softwares that do different things that have this concept of a drawing canvas, and then some menu garbage here to the left. When the desktop manager is working right, like it is right now, you can resize it. Sometimes resizing is useful. Oh, there we go. Now it's starting to lag. My internet service provider has decided that my 1 megabit per second connection speed has lasted for over a minute. Now I am belly aching. And they go back to the 27K. So I'm back to the equivalent of dial-up. Along the top are icons, which is a picture menu, just like in a fast food restaurant. So my usual one-line joke is, so if this engineering gig doesn't work out for you, at least you will be pre-trained on selecting hamburgers and onion rings, so you'll always be able to get a job. That used to be funny. I think in this day and age, maybe that's not so much humorous anymore. So we have these picture menu items, and these replicate items that are also in the top word menu program. So some of the important ones that we're going to look at are these ones. So the Puffy the Cloud is a rain gauge. There's this kind of crosshatch square. That's how we draw a subcatchment. There's these circles, which are a junction node, which will make sense as we go forward. And then there's, oh, I accidentally clicked on that. The upside down triangle is an outlet node. Every SWM model, if it's going to work, has to have at least one outlet node. A flow divider is an advanced concept that we won't get to today. Storage node is a type of junction node that has storage information associated with it. So it will have areas and depths from which volumes can be determined. The conduit link, that can be a sewer pipe, which is what it was originally intended to be, but it can also represent streams. Stream paths. There's a pump link, which in large-scale hydrology kind of doesn't make sense, but has use. Orifice, which is a type of outflow control. A weir, which is a different type of output control. And an outlet link. I don't think I've ever used that. And then the T is you can put text fields directly on the drawing, and that is sometimes quite useful. Moving on the line above, we have a file save thing, make a new folder, send stuff to the printer, which normally should always be disabled in this implementation because there's no printer attached to the remote server that I know of. There's a set of binoculars to go searching for stuff. There's a, oh, that's what that does. There's a way to turn on and off a background map. Lightning bolt runs a simulation. You can generate a status report. We'll look at that. We have the ability to generate profile plots. So this is a much different tool than HEC-HMS in its original intent and goal. However, they're both extremely useful for surface water hydrology, which is why I've included that in this lesson. So let's go ahead and attempt to do the first lesson example, which is an SCS type storm with a 640 acre watershed. So I had to bring that up for myself. Damn it, Nico. Excuse me, I got a cat in the way. Over here. There you go. Well, I'll just start. Down here in this column, in the project tab, are the different things, different parts of the SWMM model that can be included. And under options, it has the equivalence to HEC-HMS as the simulation control component. So this is where we tell what the simulation dates are, what time steps will be used, whether we can use dynamic wave model. Right now it's actually not responding to input. That's an index thing. There we go. So here's where we tell what process models will be used: rainfall runoff, rainfall dependent inflow and infiltration, snow melt, water quality. Here's where we select an infiltration model. And of these infiltration models, which ones have we examined in the course already? The trick question. We'll make it a binary question. A, all, B, none. Correct answer is A. Yeah, very good. And then there's routing. This is where we supply the information on how we want the hydraulics to behave. There's one called steady flow, kinematic wave, and dynamic wave. If you have obtained a copy of Broussard's book, and I just brought that onto the screen, you'll see that the kinematic wave is a pretty old approach, so that's actually directly stated in his textbook for the different kinds of overland flow. And then when we get to stream flow routing, so I want to skip Muskingum. Oh, it must be up here. Yeah, it's, the dynamic wave is up here in the hydraulic theory shallow water equation. So the SWMM program incorporates two of the main concepts in classic surface water hydrology as represented by Broussard's book. There's some other inputs here that we'll get to later. So like HEC-HMS, it has a frustrating date format, although it has a slight advantage in that there's ways to supply the information in elapsed time. So that makes, in my opinion, data input far easier. I have these all set to default to run for 6 hours unless you tell it otherwise. And it has to use the date and time of the server, but you can change this to reflect actual historical information. One of the common warning or errors that occur with SWMM is that the time window is wrong, and it gives a cryptic error. So I would recommend that if you get an error that doesn't make sense, especially in a simple model, go check this input dialog and be sure it's actually simulating more than 0 hours. Time steps is where you tell it how long to spend in each different thing. So this one's defaulting. It's going to report results every 15 simulation seconds, or every simulated 15 seconds of real time. In dry weather conditions, when there's no rainfall, it'll do it for every hour. And in wet weather conditions, every 5 minutes. So I'm just going to go ahead and change that. I hope I don't regret that change, but I want to make everything report every 5 minutes. And I can leave it. I'll leave that alone for now. Dynamic wave. When we actually select the dynamic wave method, we have to determine whether we want to keep inertia terms. So we can keep them, dampen them, or ignore them. If we ignore the inertia terms, we're essentially taking out the local acceleration term. We're saying it's really small, and components of the convective acceleration. The usual first step that's default is to choose dampen, which prevents them from kind of getting out of control. And then for normal flow, you can either choose it based on slope and fluid number only, or slope only. I'll just leave it with the default. In the surcharge method, we have two types. One's called X-Trend, which is described in the technical manual. The other one's called slot, which is called a Priestman slot. If you've had the open channel flow class, I believe Dr. Rainwater at least mentions in passing the Priestman slot theory. There are two different ways to accomplish a similar issue. I'll leave the X-Trend for the time being, because we're not going to be doing anything today that should matter. And then in the Files tab, you can specify additional interface files. Okay, so right now I've essentially made no changes to the defaults, except I'm doing everything on 5-minute timestamps. So the subcatchment is the tool that you use to identify a subcatchment. If I left-click and then right-click, it produces a dot. Another way to do a subcatchment is to draw it. And then this is the tricky part of the interface in SWM. So those two subcatchments in the drawing look very different. But as far as the computer program is concerned, they're the same size. The drawing in SWM is to assist you in making input structure. It is not by necessity georeferenced. You have to actually turn that feature on. I'm going to, actually I guess I'll keep subcatchment 2. I'll delete subcatchment 1. Because that drawing may be of some benefit to us. Actually, I'm going to delete them both. I'm going to attempt to load in a background. So SWM can load in bitmaps and JPEGs. So I believe I have a background map for Ash Creek as a, ooh, PDF's a gamble. We'll see if we can get that to work. I don't know if I can. Let me copy that. And I need a SWM model folder. I will tidy up the file management later. Okay, here goes nothing. So in the View menu item, there's an option called a backdrop, and you can attempt to find an image file and load it. And I'm going to see if I can get to my desktop. If I go to Computer, Z drive should be the file system. Home. Put the input again. It can't do PDF. Right. Okay, well never mind then. I'll get that fixed later. I don't have any way to convert the file type. And anyway, that's not a 640 acre watershed. So we want to do an SCS type storm. So we need a watershed. We need to choose a size, and the input units in SWM are of a much different scale than HEC HMS. If you recall our last meeting, the HEC HMS inputs are in square miles. So 640 acres, we put 1 square mile. In SWM, the inputs are in acres. And so we certainly can put a 640 here, but then we have to decide, well, how wide is a 640 acre watershed? And this concept of width is, in this particular case, sort of important. Later on, it becomes very important. And let me bring up some kind of drawing tool. What do I have I can draw? I think I can draw on graphic converter. So I'm just doing this to get a drawing tool. So in SWM, regardless of the shape of the real watershed or subcatchment, SWM takes everything as a rectangle. And the inputs you provide are the width of the rectangle, and if you know the area and you know the width, then the area divided by the width gives you a length. And the length is, oddly enough, what controls the time behavior. You can think of it as the length that a water particle has to take to get off the watershed. So width and area, I guess I'll put area here in my drawing. Width and area are what we supply as input, and length, that was a mistake. And length is what is computed. You'll also notice that there's inputs of slope and Manning's end for the overland flow. So the slope and the Manning's end and the length are what compute travel time. It's not complicated when it's explained in a drawing like this. Where it does get a little bit complicated is if the watershed is comprised, let's see if I can draw this correctly. Of 2 parts, where one side, let's say the left side is permeable and the right side is impermeable, then we have to tell the program how it's going to route things. The options are route permeable to impermeable, impermeable to an outlet, or route impermeable to permeable to an outlet, or kind of average the two and then route them both to the outlet. Usually the difference in those decisions is pretty minor, but you need to be aware of that. So that's what that length term is. Excuse me, the width term. We're back, there we go. So we have a 640 acre watershed. If it's 500 feet wide, that's real long and skinny. So I'm going to try to pick a value that makes sense. And I will just take the square root of the area in feet. Oh, my computer's now really going into go slow mode. So we have 640 acres. There's 43,560 feet squared per acre. So that's how many square feet there are. That's a bunch. So 5,280. I could have done that in my head. That's a mile. Okay, so we'll make 5,280 square feet. So I have just implicitly assumed the watershed is square. So it's going to take a mile on either side. Okay, I'll make sure there's any other data I can supply right here. Width. So we also have to supply how sloped the watershed is. I'll take the default. We can tell how much of it's impervious. I'm going to go ahead and set that to 0 for the time being. The Manning's end of the impervious, the Manning's end of the pervious, the depression storage for impervious, depression storage for pervious. I'm going to go ahead and put that into a 0. I think that can take a 0. Sub-area routing to the outlet. And currently it's set up for the Horton infiltration model. There's no groundwater component, no LID controls, there's no land uses, no initial buildup. These are for some water quality issues. No curb length. So I think that's pretty much the defaults. We have to create a rain gauge and assign it to that. So I'm going to do that next. So there's my rain gauge. I can put it anywhere in the drawing. And we'll go back here. And it didn't work. Because it's in permanent input mode now. There we go. Delete that. Yes. Looks like I got to redo my watershed, rain gauge 1. So let me get my watershed back. Fortunately, I can remember what I had to do. So here we want to put in the rain gauge 1. We don't have an outlet yet. We know the area is 640, and we determined the width was 5,280. And the 0 impervious, and I think I zeroed that out. And currently it doesn't want to obey input, which is pretty typical. Very good. Okay, I think I'll just go with that for the time being. I'll go ahead and save it because it looks like we're on the verge of a didn't really want to save there. See if we can get to our desktop. I'm going to save it right here. So now we have to tell it the name of the input file. So this is example 1. Hit save. Good. Now I can make mistakes and at least recover back to the last save. So every SWMM model has to have an outlet. And we're going to connect this subcatchment directly to that outlet. So this is a really simple SWMM model. It's actually kind of a misuse of it, but we've got to learn somewhere. Outfall. Should give us the list, but it's not going to. See if it accepted it. Press OK a few times. Come on, it's like 4 presses. Okay, we're in hang time. Good thing I saved that when I did. So it looks like SWM's pretty crashy on this server. So do what I did. Be sure you save it as you're building it. Execute. Open. Okay, so now we're back where we were. I'll go ahead and resave it and create an outfall. I'll put the outfall right there. And its name is outfall space 1. I will attempt to refuse the input. Name of the node. Okay, plan being I have to manually edit the input file. So rather than complain about the software, I'm probably making a very simple mistake. And I can't regain control. Eight 862. Well, the definition of insanity is to do it over again and again. Make a quick examination here of the input file. Try to figure out what's going wrong. Say catchment, rain gauge. Got 2 outlets. We will try one more time. I'm going to put a node in and see if I can route to the node. So, properties. See, the outlet's supposed to give us a pull-down menu just like this. And it's clearly not doing that. See if junction 1 will work. Oh, okay, cool. Let's see if I can turn that into an outlet node. That wasn't what I wanted to do. Let's try this one more time. Right click, convert to outfall. Right click, convert to outfall. There we go. Now we have a model I want. Go ahead and save everything. Press the save icon. See if it will redraw correctly. Okay, very good. So our watershed's right here, our outfall's right here. There has to be an outfall for the program to run. In this instance, the outfall isn't very informative, other than it has to be there. What we'll do is we'll get the flows of the outfall and see how that looks. So our next thing is our rain gauge. And we have to determine what type of input, whether we want to put intensity, which is like inches per hour, volume, which is going to be a depth, so inches at different moments in time, or cumulative, which is the way that, which was the blue line when we looked at the rainfall representation. I'm going to leave it at intensity for the time being. And then we have to tell it the time interval. In this case, it defaults to every hour. Data source is time series. Our options are time series or an external file. We're going to use time series, and we have to name the series. So SCS. Hopefully it can handle the space. Oh, it's like really... and we can put a description here. We'll call it SCS storm. We can have a column for the date, a column for time, and then the value. So what I personally like about SWM is if I don't want to use calendar days, all I have to do is enter time. And as long as it's monotonically increasing, it does it as simulation time. So the next thing we can do is get an SCS storm. And where might one of those be? It's actually contained in SWM. It's not SWM, we're in SWM. It's actually contained in Pick HMS. It was our example one. I'm going to go ahead and actually run the HMS program simply to get an output file. Hopefully it saved it. I don't have to rerun the simulation. Oh, that was wishful thinking, wasn't it? Okay, let's see if we can break this time. And I want that. I want the time series table. So I am looking for this column right here. And I really probably just need 24 hours. Hopefully the buffer is big enough. These are in 15 minutes. Hit a copy. Oh, that was good. So now we've got the time series, and the first one we'll just set at 0. And now we want to get our time window. I guess I should have grabbed them both at the same time, but I was afraid of the buffer being too small and having it crash the whole thing. So now I'm just going to grab think I started at 0. And it's okay, 23:45. We'll include the 24th hour. And we'll put a value of 0.03. Let's take a look at it. And there's our time series. It looks very much like it did in Heck HMS because it's basically taken from Heck HMS. Let's hit OK. That saves it. Actually, I'm going to save everything now. Now I'll go ahead and put this back in the correct time interval, which is 15 minutes. Save everything again. And we are set to go. So if you remember in our options, we set the storm up for, I have it set default at 6 hours. We'll go ahead and make it a 24-hour run. Do it again. Okay, so it's being snotty. There, that should be 24 hours. Press the OK button, save it. Okay, that was a lot of setup for something pretty simple, but we're now ready to attempt to run the simulation. I don't think it matters what routing method I've chosen, so I'm going to just leave whatever's there in the defaults. Let me check the reporting times. Okay, nothing interesting there. Time steps are all set at 5 minutes, so we're good to go. What part of close didn't you take? There you go. So now we'll attempt to run it. So there's the usual 3 things can happen. It'll run, and it'll get done, and then we can look at the output. There'll be some kind of error, or it'll just hang. I'm pretty sure it's going to run. And so this is a successful run. It tells us the run was successful. Doesn't mean we got everything right, but it means it was able to do calculations and get to a scheduled end of calculation. So if we look at OK, we can select the subcatchment, and we're going to attempt to produce a time series plot on the subcatchment using the built-in plotting tool. So the default for a time series plot for something like a subcatchment is runoff. So we'll accept the default. And the runoff is a lot different looking than when we did it in Heck HMS. Let's look at the HMS result. And the reason being is the HMS one had no transformation in it. So here's what the HMS one looks like. And there's the SWM one. And in the SWM one, the maximum runoff was 30 cubic feet per second. And in HMS, it was 7,000 cubic feet per second. So that's clearly a difference, and we would have to diagnose why that is. That's much different behavior than I would have expected. So I have an input error. I have a conceptual error somewhere in the SWMM representation. Let's see, I will shrink that and see if I can figure my conceptual error. Okay, we got the area right, width right, pretty low slope. I'm okay with all that. That probably won't make much of a difference. Oh, I have Horton's, I have an infiltration method that's active. Let's see what happens if I turn that off. That's in options, general, rainfall runoff. So we don't have a choice of turning it off, but we can play a game on it. I'm going to switch to curve number, and I'll put a curve number of 100, which essentially has no runoff, no loss component to it. I will attempt to edit it, and it will refuse me. There we go. So I'm going to put a curve number. Hopefully it will accept the 100. If 100 won't, well, 1,000 would be a stupid thing. If the 100 will not work, I'll put 99 in. So let's see if it will accept 100. It has error checking. So it accepted that as input. Let's go ahead and save that. Save it again because I'm not sure it took the save. And we will rerun the project. Choose OK. Let's look at the time series now. It should redraw automatically. Okay, so that's a different behavior. We're still getting only 160 cubic feet per second runoff. So we want to ask ourselves, why is that? And so the next thing to look at would be the rainfall. Perhaps even though we copied it directly, we may have copied the wrong column. So the column we wanted to copy, so we did inches. We didn't do inches per hour. So the next aha is, let's adjust the rainfall into the correct units. So we go to study area map, rain gauge, and inches is the volume representation. So now I expect a runoff in the thousands, or something else will break. Bring the graph back up. Well, it's still not in the 7,000s, but it's starting to look more like one would expect it to. And so that's a fundamental difference between SWMM and HEC HMS on, I'm going to look in the, yeah, there's 1/7,000 in the HEC HMS at noon, at 12 o'clock. There should be a depth of 2.78 inches. So let's see if we have that in our SWMM model. Because at this point, that's the only explanation of the differences. We've modeled the same process, so we should get roughly the same output. So we'll take a quick look at that. Properties. And look at the actual time series. We want to go to 12, 2.78 inches. That part looks correct. So our rainfall input is as expected. Our time interval, I think those are 15 minutes. Yeah, they must be because they have the correct length. So let's look at the status report. This is where we'll report mass balance errors, and we need to find out where the mass balance error is. So here's what's coming in: 531 acre-feet and 461 acre-feet is runoff. It's still getting infiltration loss. There's a problem right there. So I got another plan. Now we have to get really clever with our hydrology. Because it's generating infiltration losses, which is not correct, we need to shut that down. So let's see what's the fastest way to do that. I'm going to risk breaking it. So what I'm going to do is I'll go back to Horton's method. And I will put in parameters which should prevent infiltration. Okay, maximum rate. I can't get it to 0, but I can get it really small. So now we should get closer to that 7,000 CFS. That wasn't what I expected, but I still have a fair amount of infiltration loss. The other difference is I still have 64 acre-feet of storage on the watershed. But that still doesn't explain, in my opinion, the runoff behavior. So while we've modeled the same process, we got different answers. That's not necessarily surprising, but the application of it would dictate what we do next. So clearly the HMS model seems to make sense in terms of direct rainfall to runoff, but if we went ahead and incorporated some kind of routing, and let's try kinematic wave is going to be the closest. Let's see if I can fake this. So, oh, I can't come up with those inputs in a hurry. Let's go ahead and put an SCS hydrograph in it. We have 0.5% slope, a mile length, so that would be a mile a minute is, excuse me, mile an hour should be about right. So it should take about 60, come on, what part of yes don't you understand? It should take about 60 minutes to generate runoff. I'll go ahead and put 60 minutes in there. Rerun this. Look at the output. Now we're on comparable behavior. So this is predicting a peak of around 2,000 cubic feet per second, and its swim I think is at 1,400. So still not the same model, but quite a bit closer. 12 to 1,400. Okay, so at this point we've seen how to model very much similar situations in two different tools. We also learned something valuable. I'm about to conclude the video. What we learned is that even though we thought we were modeling the identical situation, we weren't. And it's because of the conceptualizations of the two different tools. They were never designed to do the same thing. So we have to apply some human intellect to coax them into our best conceptualization of the same process. And so what we discovered was that to make HEC HMS and SWM model what we think of the same process, HEC HMS had to have a transport component. In the case of SWM, the other way we could have done SWM, I'll take the remaining 4 minutes. So turning HEC HMS off again is pretty easy. We go to section subbasin, we turn the transform method to none. I'll rerun it, and we'll get back to 7,000 CFS or something. Rerun it again. Rerun it again. This time it's... Okay, so there is no process model. The closest we can get to SWM for no process model in terms of transform is, remember that width that I spent so much time on? If we make it really wide, so right now the width is 5,280, and so is the length. If we make the width, say, 100 times bigger, the length should be 100 times smaller. Maybe it's 1,000. Now if we run it, we should get much different output. And so we made a very wide, skinny watershed, almost immediate transport to the outlet. And now the discharges are starting to agree. So the point of all that was, it's not a trivial exercise to switch between two different modeling tools, especially when they came at different times in history and their primary role is to do different things. Nevertheless, they can model the same situations if they're conceptualized correctly within the model tool. And I intend to spend the rest of the class, the next several weeks, of trying to illustrate differences like this. And I'm not trying to encourage one modeling tool over the other. In my personal opinion, each has their advantages. I am much more of a SWM user because my career has spent more time in the hydraulics management side of hydrology. But HEC HMS is a useful tool, and it has some advantages in that the hydrologic conceptualizations of things where methods are turned off is a whole lot more sensible than in SWM when you're having to create conceptualizations that don't make much physical sense. And so with that, I will conclude today's meeting. I will independently record the first 9 minutes so you can see the PowerPoint slides, but they're not special. And I will take up the Ash Creek simulation next time. That'll only take a few minutes because we've got the hard work done. We're basically going to use the same input file, but we'll modify it for the Ash Creek. And I'll prepare a JPEG for a background because it'll make it a little easier to discuss. So with that, if there's no questions, I'll open it up for a few questions as I'm preparing to shut everything down. And like I said at the beginning, which I think was not recorded, I'll get all the links on the Moodle site. They're not active right now. That's my bad. Okay, I think if I close that, it's going to ask me if I want to save everything. I'll choose DA. Yep. And I'll go ahead and put copies of this onto the content website so that if if you're having difficulties, you can just download the input file and run it in SWM directly. If there's no questions, there'll be a homework assignment up by the end of today. It's really quite straightforward. I'm asking you to make some evapotranspiration estimates for Dallas, Houston, and San Angelo. There's nothing special about those three areas per se, but the example problems I'm using are either from Dallas, Houston, or actually Eden, Texas, which is 70 miles east of San Angelo. So those 3 areas will be useful background for further examples. So that's mainly why I'm asking you to do it, as well as to get a little confidence that you can do something like that pretty rapidly. The third part of the exercise is to go to that Texas Water Development Board website and download the evaporation data for those 3 areas. I've identified the grid cells that I think are correct for it, and compare the data science result with the Thornwaith and Blaney Cribble. So when I send out the invitation for the lesson tomorrow, I'll include the links to those exercises. That's all going to be sent in a single email. And have a great afternoon, everybody. Thank you for your patience and attention, and thank you for telling me to share the screen, and thank you for telling me to turn on the recording, because that would have been a total Monday at that point. Are there any questions? Very good. I will. Yeah, it would help if I turned the chat on in the future. I will see you tomorrow. Have a great day.